Our own galaxy holds secrets that defy everything we think we know. The Milky Way is not a quiet cosmic home, but a stage for phenomena so strange they challenge the very laws of physics. By the end of this journey, you will understand the 25 greatest mysteries that astronomers are still struggling to solve. We will explore a black hole that behaves unlike any other and confront a ghostly substance that makes up most of our galaxy yet remains completely invisible. What cosmic puzzle do you find most compelling? At the very heart of our galaxy lies a paradox. Sagittarius A, the supermassive black hole anchoring the Milky Way, should be a beacon of ferocious energy. With a mass 4 million times that of our Sun, its gravitational pull is unimaginable. Yet, when we point our telescopes toward it, this cosmic giant is curiously quiet. It flickers with faint flares of light and X-rays, like a candle sputtering in a vast, dark hall. For an object of its immense power, it is astonishingly dim, almost as if it is on a strict cosmic diet. Astronomers are baffled by this lack of appetite. One theory suggests it is merely in a dormant state, a sleeping dragon between feeding frenzies. Another, more radical idea posits that our understanding of physics itself is incomplete, that exotic processes we have not yet discovered are at work around its event horizon, somehow suppressing its energy output. Adding to the strangeness are the peculiar G objects whirling around it. These enigmas look like bloated gas clouds, but they move with the precise orbits of stars, skating perilously close to the point of no return without being shredded by the black hole's incredible gravity. What are they, this hybrid of star and cloud, and what secret do they hold about the extreme environment at our galaxy's core? But our galaxy is not an island adrift in stillness. It is caught in a current, pulled by a force so immense it defies easy comprehension. We are all moving at over 1 million miles per hour toward a cosmic phantom known as the Great Attractor. This colossal gravitational anomaly lies in the distant sky, in the direction of the Centaurus and Hydra constellations, and it is not just tugging on the Milky Way. Thousands of other galaxies are flowing with us in this vast, silent river through space, all drawn toward a point we cannot clearly see. The biggest obstacle to understanding this phenomenon is our own home. The Great Attractor lies directly behind the plane of the Milky Way, a region astronomers call the zone of avoidance. Here, the thick dust and countless stars of our galaxy's central disk create a cosmic fog, blocking our view of the universe beyond. It is like trying to see a distant mountain range through a dense, personal storm cloud. For decades, this hidden monster was little more than a ghostly tug in the data, a gravitational signature without a clear source. What could possibly possess such power? The leading theories are as staggering as the pull itself. One possibility is that it is not a single, unimaginably massive object, but an immense supercluster of galaxies, a gathering of cosmic islands so vast that its collective gravity dictates the motion of our entire galactic neighborhood. Another, more mysterious idea suggests the heart of the Great Attractor could be an extraordinarily dense knot of dark matter, the invisible stuff that binds the cosmos, exerting its influence without ever revealing a single light. The quest to unveil this secret is far from over. New telescopes equipped with instruments that can see through the obscuring dust in infrared and radio wavelengths are now mapping the hidden structures behind the zone of avoidance. With every new observation, we peel back another layer of the cosmic fog, inching closer to identifying the true architect of this million-mile-per-hour journey. What will we find when we finally gaze upon the source of this immense river in the sky? This silent pull toward the Great Attractor hints at a far greater, more pervasive presence hidden in plain sight. Our galaxy is cocooned within a ghost, a vast spherical halo of dark matter that outweighs every star, every planet, every speck of visible dust by a factor of 5 to 1. This is not a small discrepancy. For every single ounce of the universe we can see and touch, there are 5 ounces of something else, something completely invisible and utterly mysterious. We only know this phantom exists because of its gravity. Stars on the outer edges of the Milky Way's spiral disk are orbiting at speeds that defy logic. According to the laws of gravity, these distant stars should be moving much more slowly, like planets in the outer solar system that take centuries to complete a single orbit. Instead, they are whipping around at velocities so high that they should be flung off into intergalactic space. The only explanation is that an enormous amount of unseen mass is holding them in its gravitational grip, a cosmic glue we call dark matter. We see its fingerprint again in the way it bends the fabric of space-time, distorting the light from distant galaxies behind it in a phenomenon known as gravitational lensing. It is there, it is real, and it shapes the very structure of our galaxy, yet it refuses to interact with light or normal matter in any other way. It simply passes through everything, including you and me, as if we were not even there. So what is it made of? The leading candidates are as elusive as the substance itself. For decades, physicists have searched for weakly interacting massive particles, or WIMP. These hypothetical heavy particles would rarely bump into normal atoms, explaining why they are so difficult to find. To hunt for them, scientists have built incredibly sensitive detectors placed deep underground, in old mines and beneath mountains, where they are shielded from the constant rain of cosmic rays that could mimic a dark matter signal. They wait in profound silence and cold for the once-in-a-lifetime tremor that might be a WIMP gently colliding with an atom. Another compelling candidate is the action, a particle so light and ghostly that trillions of them could be passing through your hand every second without you ever noticing. Specially tuned resonators are now scanning the cosmos, listening for the faint radio wave whisper of an action converting into a photon in the presence of a powerful magnetic field. From the depths of the Earth to the void of space, the search for this cosmic phantom continues, a quest to identify the true architect of our galaxy's form and motion. What will it reveal about the fundamental nature of reality when we finally trap this shadow? Yet this invisible dark matter halo is not the only ghostly structure shaping our galaxy. Emanating from the very core we just explored, two colossal orbs of energy balloon outward, stretching for 25,000 light-years above and below the galactic plane. These are the Fermi Bubbles, immense twin structures glowing faintly in the highest energy form of light, gamma rays. They were completely unknown to science until the Fermi Gamma Ray Space Telescope mapped the entire sky, revealing this faint but gigantic hourglass figure superimposed on our Milky Way. The sheer scale of these bubbles is difficult to grasp. Each one is a cosmic cavity so vast that it would take a beam of light 25,000 years to travel from its base at the galactic center to its outer edge. Creating such enormous structures required a cataclysm of almost unimaginable power, a blast of energy that must have rocked the entire galaxy. What event could have possibly forged these titanic balloons? The most tantalizing suspect is the sleeping giant at our galactic center, Sagittarius A star. Some scientists propose that millions of years ago, this supermassive black hole awoke from its slumber in a spectacular outburst. It may have devoured a vast cloud of gas or perhaps an entire star, and in the process, it belched out two opposing jets of superheated matter and radiation at nearly the speed of light. These jets would have punched through the galaxy's gaseous halo, inflating the Fermi bubbles like a cosmic glassblower shaping a delicate sphere. This ancient eruption would have been a brief but terrifying event, a flash of cosmic violence whose echo we only now detect as a faint gamma-ray glow. But the black hole is not the only possible culprit. Another theory points to a different kind of frenzy at the galactic center, a period of intense star formation known as a starburst. In this scenario, thousands of massive stars were born in a short, violent period. These stars lived fast and died young, exploding as supernova in a continuous, rolling thunder of detonations. The combined energy from all these stellar deaths could have blown a gigantic collective wind, sweeping up material and energizing it to create the bubbles we see today. There is an even more exotic possibility, one that connects back to the dark matter enveloping our galaxy. Some physicists speculate that the bubbles could be the signature of dark matter itself. If these invisible particles are their own antimatter counterparts, they might annihilate upon contact, transforming their mass directly into pure energy. A dense concentration of dark matter at the galaxy's core could provide the fuel for such a process, creating a steady outpouring of energy that slowly inflated these vast structures over eons. Pinpointing the true cause remains one of astrophysics' great challenges because the evidence is so old and diffuse. We are essentially looking at the fossil of a galactic-scale explosion, trying to decipher the murder weapon from the shape of the crater. Did a single, monstrous eruption from the central black hole create them in a geological instant, or was it the combined wind from a million dying stars? Or are we witnessing the faint, steady glow of the universe's most elusive substance finally revealing itself through annihilation? The Fermi Bubbles stand as a silent monument to a violent chapter in our galaxy's history, a mystery written in gamma rays across 50,000 light-years of space. While the silent glow of the Fermi Bubbles represents a cosmic mystery on an epic scale, one of our most tantalizing enigmas arrived as a fleeting shout in the static. On a quiet Ohio evening in August of 1977, a radio telescope known as the Big Ear was steadily scanning the sky, its singular purpose to listen for any sign we are not alone. It was a routine night, its data printed line by line on continuous fanfold paper. But then something extraordinary happened. For 72 seconds, the telescope's receiver was flooded with an intense, focused burst of radio waves. This was not the gentle hiss of a distant star or the messy broadband crackle of a natural cosmic event. It was a pure, narrowband signal, concentrated on one specific frequency, precisely the kind of signature you would expect from an engineered interstellar beacon. The signal grew in strength as the telescope's field of view drifted onto it, peaked with stunning intensity, and then faded away as the Earth's rotation carried the Big Ear's gaze past it. It was gone as suddenly as it had appeared. Days later, astronomer Jerry Amon was reviewing the printed data, his eyes scanning the columns of letters and numbers. There it was, a sequence so strong and so perfect that it stood out from the background noise like a flare in the night. In a moment of pure astonishment, he circled the alphanumeric string and, in the margin, simply wrote one word. Wow, that single, human expression of wonder gave the signal its name and cemented its place in history. The wow signal remains the most compelling candidate for an artificial transmission ever detected. Its frequency, 1420 MHz, is a protected band, a quiet channel where earthly transmitters are forbidden to broadcast, making accidental human interference unlikely. It came from a region of space near the constellation Sagittarius, a direction relatively empty of stars, which only deepens the puzzle. The hunt for a repeat has been relentless. For decades, astronomers have pointed powerful radio telescopes back toward that same patch of sky, listening for another whisper, another confirmation. They have heard only silence. The search for a natural explanation has been just as thorough. Could it have been a signal reflected off a piece of space debris? The frequency and duration do not match any known satellites or spacecraft. Was it a comet? 2 comets were later identified in the general area, but their faint, diffuse gas clouds are incapable of producing such a powerful, focused burst on that specific radio band. Every proposed solution has crumbled under scrutiny. The wow signal endures, a singular event that has never been replicated. It was a perfect cosmic hello that lasted just over 1 minute, a shout into the void that we happened to be in the exact right place at the exact right time to hear. It is a ghost in the machine of science, a piece of data that refuses to be explained away, leaving us with a profound and haunting question. Were we, for one brief moment, listening to another civilization? While the wow signal was a fleeting whisper from the void, other cosmic messages are written in the blinding speed of stars themselves. Some stars are not content to circle our galaxy in orderly orbits. They are renegades, cosmic fugitives racing through the darkness at over 1 million miles per hour, so fast they are leaving the Milky Way behind forever. These are the hypervelocity stars, and their incredible journeys begin with one of the most violent gravitational mechanisms in the universe. The most widely accepted theory points a finger directly at the sleeping giant at our galactic center. Imagine a binary star system, two suns locked in a graceful dance around each other as they have been for billions of years. This stellar pair drifts too close to the supermassive black hole, Sagittarius A. The black hole's immense gravity violently tears the binary apart. In a cosmic game of gravitational pinball, one star is captured by the black hole, forced into a tight, doomed orbit. Its partner, however, receives an immense slingshot of energy, a kick so powerful it is flung outward at a significant fraction of the speed of light. This star becomes a lone projectile, its trajectory set on a one-way trip out of the galaxy. The existence of these stars is more than just a spectacular curiosity. They are celestial probes carrying vital information about the galaxy they are fleeing. As a hypervelocity star races through the Milky Way's halo, its path is subtly bent by the gravitational pull of the invisible dark matter that permeates everything. By carefully tracking the trajectories of these stellar escapees, astronomers can essentially use them to map the distribution and density of the ghostly dark matter that would otherwise remain completely hidden from our view. Each one is a tracer, its flight path revealing the contours of the unseen gravitational landscape. This is why the hunt for more of these cosmic speedsters is so intense. Every new hypervelocity star discovered is not just another data point. It is a potential messenger from a past cataclysm at the galactic core. By tracing their paths backward through space, we can potentially pinpoint violent events in the history of Sagittarius A, moments when it feasted and flung stars across the cosmos. They are living fossils, their incredible speeds a permanent record of a long-ago encounter with the most destructive force in the galaxy. What other tales of cosmic violence are these runaway stars carrying into the endless dark? These stellar fugitives race through a galaxy that is itself moving through an even grander emptiness. We are not merely adrift on a river toward the Great Attractor. Our entire galactic neighborhood floats within an immense cosmic bubble, a void of staggering proportions now known as the KBC void. This is not a void of pure nothingness, but a region of space where galaxies are far fewer and farther between than the cosmic average. It is a vast underdense sphere, a bubble in the foam of the universe, and we are nestled deep within it. The scale is almost impossible to comprehend. The KBC void stretches for roughly 2 billion light-years across, making it one of the largest structures ever identified. For context, our entire Milky Way galaxy would be a mere speck within this colossal emptiness. This discovery directly confronts one of astronomy's most fundamental tenets, the cosmological principle. This principle asserts that, when you look at the universe on a sufficiently large scale, it should appear roughly the same everywhere. There should be no special places, no grand centers or edges, just a uniform distribution of matter and energy. The existence of a void this immense, with us sitting right in the middle of it, seems to challenge that very idea. It raises a provocative question. Are we, against all philosophical odds, in a uniquely sparse location? The implications of our address inside this void are profound, especially for our attempts to measure the universe's expansion rate, a value known as the Hubble constant. Think of it like this: if you are in a region with less gravitational pull from surrounding matter, the local fabric of space might be expanding at a slightly different rate than the denser universe beyond our bubble. Our measurements of how fast other galaxies are receding from us could be skewed by this local emptiness. We might be getting a slightly inflated value for the expansion rate, simply because the space in our immediate neighborhood is stretching a bit faster. This could help explain one of the biggest headaches in modern cosmology, the Hubble tension, where different methods of measuring the universe's expansion yield stubbornly different results. Could our place inside this cosmic bubble be throwing off the cosmic scales? Not all astronomers are convinced the KBC void is the definitive answer. Some argue that while the void is real, its effect on the Hubble constant is relatively minor, a small correction rather than a paradigm-shifting discovery. Others scrutinize the data, questioning if the underdensity is as pronounced as the initial findings suggest. The debate is fierce, a classic scientific clash between a foundational principle and a potentially disruptive observation. Are we truly seeing a flaw in the cosmological principle, or is the universe simply more complex and foamy than we ever anticipated, with voids and filaments on scales we are only beginning to map? Our galactic home, it seems, resides in a quiet backwater, a cosmic suburb whose emptiness might be silently shaping our entire view of the universe. Our quiet cosmic suburb hides a violent past. The serene spiral of the Milky Way is not a pristine structure but a testament to a history of consumption, a story of galactic cannibalism written in starlight. For billions of years, our galaxy has grown not just by making its own stars, but by devouring its smaller neighbors. We are a cosmic melting pot, and the evidence of these ancient feasts is scattered all around us. One of the most dramatic examples is unfolding right now, a slow-motion collision with the Sagittarius dwarf elliptical galaxy. This tiny companion galaxy is caught in our immense gravitational pull, and it is being systematically torn apart. As it swings around the Milky Way, our gravity strips away its stars, pulling them into long, shimmering rivers of light that wrap around our galactic disk like ribbons on a maypole. These are stellar streams, the ghostly remnants of a galaxy being digested. You cannot see this with the naked eye, but our telescopes reveal these faint trails, tracing the final orbits of a doomed celestial system. This ongoing destruction provides a living laboratory for understanding how galaxies grow. The Sagittarius dwarf is like a clock, its dismembered body allowing astronomers to measure the gravitational field of our galaxy's dark matter halo with incredible precision. The way the stream is stretched and distorted maps out the invisible forces shaping our home. But this is just the latest chapter in a long and violent biography. The forensic evidence of past mergers is etched into the very fabric of the Milky Way. Some of the oldest star clusters in our galactic halo, known as globular clusters, move in strange, distorted orbits that betray a traumatic origin. They were not born here. They are cosmic orphans adopted during ancient collisions and now swirling around the galaxy's outskirts. Even the chemical makeup of stars tells a story of different origins. Stars born in the Milky Way have a specific chemical fingerprint, rich in heavier elements forged in stellar furnaces over eons. But astronomers have identified many stars with a distinctly different composition, lower in these metals, a signature that points to their birth in smaller, more primitive galaxies that were later consumed. Their unique chemistry is a tag from a foreign shore, a permanent mark of their extragalactic origin. The aftermath of these mergers can be seen in the very structure of our galaxy's disk. Immense gravitational waves from a passing dwarf galaxy can create ripples like a stone thrown into a pond, perturbing the orbits of millions of stars. Recent surveys have actually mapped these vast, wave-like disturbances coursing through the Milky Way, a lingering vibration from a collision that occurred billions of years ago. Each piece of evidence, from the faint stellar streams to the chemical tags in ancient suns, helps astronomers piece together a family tree of violence. The serene Milky Way we see on a clear night is a mosaic, a collage of countless smaller galaxies that were absorbed over cosmic time. Our galactic home is not a solitary island, but a cannibal, its majestic spiral arms built from the remnants of its former neighbors. What other ghosts of devoured galaxies are hiding in plain sight, waiting for the right telescope to reveal their stories? The violent history of our galaxy's growth is written in the cannibalized stars around us, but a different kind of gravitational story is unfolding much closer to home, in the frozen darkness beyond Neptune. Far past the orbit of Pluto, in a region known as the Kuiper Belt, thousands of small, icy worlds circle the Sun in what should be random, scattered orbits. Yet a handful of these distant objects are behaving strangely. Their elongated paths around the Sun are mysteriously clustered, as if an unseen shepherd is herding them, guiding their movements with an invisible hand. The orbits of these extreme Kuiper Belt objects are tilted and grouped together in a way that defies the gravitational influence of the known planets alone. The most plausible explanation for this bizarre orbital alignment is a hidden world, a massive planet several times the size of Earth lurking in the perpetual twilight of the outer solar system. Astronomers have dubbed this hypothetical giant planet 9. Its predicted orbit is immense, taking perhaps 10,000 or even 20,000 years to complete a single, slow journey around the Sun. At such a staggering distance, it would receive virtually no sunlight, a cold, dark ghost world drifting through a region we have only begun to map. Finding this phantom planet is one of astronomy's greatest modern challenges. Spotting an object that faint and that far away is like trying to see a single piece of coal in the pitch black of a moonless night from thousands of miles away. You would not know exactly where to look, and even if you were staring right at it, it would barely register. This is the monumental task facing astronomers. They are using the world's most powerful telescopes, like the Subaru telescope in Hawaii, to conduct a painstaking, square-by-square search of the vast sky region where Planet 9 is predicted to be. They are looking for the tiniest pinprick of motion, a slow-moving dot that shifts its position against the backdrop of fixed stars over nights, weeks, or even months of observation. Each potential candidate must be tracked and verified, a process that rules out distant stars, asteroids, and other celestial imposters. The discovery of Planet 9 would be a revolution in planetary science. It would force us to completely rewrite the story of our solar system's formation and dynamic history. How did a planet that large end up in such a distant, tilted orbit? It may have been flung outward during the solar system's chaotic early days, a dramatic event that reshaped the entire planetary family. Its presence would also explain other solar system puzzles, like the unusual tilt of the Sun's axis. This would confirm that our cosmic neighborhood is far more dynamic and complex than we ever imagined, with a hidden giant still waiting to be found. Is Planet 9 truly out there, a frozen titan silently shaping the fringes of our own star system, its gravitational whispers the only sign of its immense presence? The gravitational whispers of a hidden planet are not the only strange signals echoing through our galaxy. Sometimes the cosmos shouts, imagine the entire energy output of our Sun, released not over days but compressed into a single, blinding millisecond. This is a fast radio burst, an explosion of radio waves so intense it can outshine entire galaxies. And for years, they were one of the universe's most perplexing riddles because they all seem to come from impossibly distant galaxies. That all changed in April of 2020 when a cataclysm occurred right here in our own cosmic backyard. A magnetar known as SGR 1935+215 erupted. This was not just any dead star. A magnetar is a specific type of neutron star, the collapsed core of a giant sun, but with a magnetic field so powerful it defies comprehension. Its magnetic pull is a quadrillion times stronger than Earth's, a force so intense it could strip the information from every credit card on our planet from halfway across the Milky Way. This particular magnetar, located about 30,000 light-years away, unleashed a double blast. It shot out a mix of X-rays and, crucially, a brilliant millisecond flash of radio waves. For the first time ever, we had caught a fast radio burst in the act, and it was coming from a known, highly magnetic stellar corpse within our own galaxy. The discovery was a monumental breakthrough, finally providing a solid identity for at least one type of these cosmic firecrackers. The theory is as violent as the event itself. These magnetars are thought to undergo what are called starquakes. The neutron star's incredibly rigid crust, under unimaginable stress from the twisting magnetic fields within, suddenly fractures. This seismic event on a stellar scale releases a colossal amount of pent-up energy, shaking the magnetic field and accelerating particles to near light speed, which then blast out that telltale flash of radio waves we detect as an FRB. It was a perfect match, a solution to a decade-long mystery. But did this one discovery solve the entire puzzle? Far from it. The detection of a galactic FRB was like finding a single culprit for one local crime, only to realize a global crime wave is still underway. The magnetar burst we saw was powerful, but it was actually on the weaker end of the FRB spectrum. Many of the bursts coming from other galaxies are thousands of times more energetic. Could a magnetar's quake really account for that level of raw power? Furthermore, astronomers have since observed something even more bizarre, repeating fast radio bursts. These are sources that flash again and again, sometimes in predictable patterns, sometimes at random. A one-time starquake makes sense, but a source that cracks repeatedly over years is much harder to explain with a single catastrophic rupture. It suggests a different, more durable engine, perhaps involving material falling onto a highly magnetized neutron star or interactions within a dense star cluster. So while we finally have a confirmed actor in this cosmic drama, the magnetar, the plot has only thickened. It appears the universe has multiple ways of creating these brilliant, fleeting shouts. Some are the death cries of singular stars, while others may be the persistent, repeating beacons from exotic systems we are only beginning to understand. The Galactic FRB gave us a key, but it opened the door to a room far larger and more mysterious than we ever imagined. What other cosmic machines are capable of such concentrated, instantaneous fury? The same violent history that scattered our galaxy with stellar streams left behind an even more profound mark, an ancient giant buried in the very motions of the stars around us. A decade ago, the European Space Agency's Gaia Observatory began its ambitious mission to map the precise positions and movements of over 1 billion stars, creating a living, three-dimensional atlas of the Milky Way. When scientists dove into this unprecedented data, they found a ghost. A specific population of stars, millions of them, were not moving in the gentle, circular orbits typical of the galactic disk. Instead, they were streaming along highly elliptical, radial paths, diving in toward the galactic center, and then soaring back out to the distant halo like a swarm of cosmic bees. Their collective motion was so distinct that when plotted on a chart, it formed a long, hot dog-shaped structure, quickly earning it the memorable nickname, the Gaia sausage. This was no random grouping. It was the fossilized signature of a cataclysm from the dawn of our galaxy. Astronomers realized they were looking at the remains of a dwarf galaxy, now formerly called Gaia Enceladus, that collided with the young Milky Way around 10 billion years ago. This was not a glancing blow. It was a head-on, transformative merger, a cosmic fender bender of epic proportions that fundamentally reshaped our galactic home. The energy from this colossal impact was so immense that it violently stirred up the primordial gas and stars of the young Milky Way, puffing them up to form what we now know as the galaxy's thick disk. Before this discovery, we saw the thick disk as a simple structural component. Now we know it is a relic of a traumatic birth, a permanent scar from a long-ago collision. The stars of the sausage itself did not simply disperse. they were shredded and incorporated, their unique, plunging orbits becoming a permanent part of our galaxy's gravitational fabric. Today, these stellar immigrants make up a substantial portion of our galaxy's halo, meaning a significant fraction of the stars orbiting the Milky Way's outskirts are not native-born, but refugees from this single ancient event. How does this change our story? The Gaia sausage rewrites the Milky Way's origin. It reveals that our galaxy did not grow slowly and peacefully. Its mature, spiral structure was forged in a violent youth, a defining merger that set its architecture for billions of years to come. Every time we look at the broad, diffuse band of the Milky Way's thick disk, we are seeing the echo of a 10-billion-year-old crash, a ghostly sausage of stars that helped build the galaxy we call home. That ancient stellar collision is written into the very chemistry of our galaxy's oldest suns. Deep within the atmospheres of these primordial stars lies a chemical mystery that reaches all the way back to the universe's first moments. It is called the lithium problem, and it is a fundamental crack in the story of our cosmic origins. According to our most precise calculations of the Big Bang, the nuclear furnace of creation should have forged a specific amount of the light element lithium alongside hydrogen and helium. The universe's oldest stars, which formed from this pristine primordial gas, should act as perfect cosmic time capsules, preserving that original lithium abundance. Yet when astronomers measure it, they find only about 1/3 of the predicted amount. It is as if a cosmic thief stole 2 out of every 3 lithium atoms from the infant universe. This is not a small accounting error. It strikes at the heart of Big Bang nucleosynthesis, the process that created the first atomic nuclei in the initial 20 minutes of everything. If our theory of the universe's birth is correct, the numbers should match. The fact that they do not mean something is profoundly wrong. Either our understanding of nuclear physics in those first frantic minutes is incomplete, or something happened to the lithium after the stars formed. Could new, undiscovered particles provide the answer? One compelling idea involves actions, the same ghostly particles proposed as a candidate for dark matter. Theorists suggest that if actions exist, they could have been produced in the early universe and subtly altered the nuclear reactions, reducing the final lithium yield. Alternatively, perhaps our models of the stellar interiors themselves are flawed. These ancient stars are not simple, inert fossils. They are dynamic engines, and lithium is a fragile element. It is destroyed at temperatures far lower than those found in a stellar core. It is possible that slow, churning currents deep within these old stars drag the surface lithium down into hotter layers where it is simply burned away, erasing the primordial signature over billions of years. But why would this happen in some stars and not others? The puzzle deepens with the discovery of a few rare, ancient stars that do, in fact, show the full, predicted amount of lithium. This suggests the destruction process is not universal, adding another layer of complexity to the mystery. The lithium problem remains a stubborn, unresolved thorn in the side of cosmology. It forces us to question our most fundamental narrative, from the particles that flitted through the newborn cosmos to the inner workings of the universe's first stars. What other secrets about creation are hidden within the faint light of these ancient suns? This galactic puzzle of ancient lithium connects to a much larger cosmic question, one that challenges our understanding of how galaxies are even built. For decades, astronomers believed they had a fundamental rule, a cosmic scaling law linking a galaxy to the monster in its heart. The bigger the galaxy's central bulge of stars, the bigger its supermassive black hole should be. It was an elegant, predictable relationship, suggesting that galaxies and their black holes grew up together, their fates intertwined across cosmic time. Then we found the exception, a galaxy called NGC 1277, and the rulebook was thrown out entirely. Located 220 million light-years away, this lenticular galaxy is a relic, a frozen snapshot of the early universe. And at its core lies a behemoth, a black hole so disproportionately large it defies all logic. While our own Sagittarius A star makes up a tiny fraction of our galaxy's central mass, the black hole in NGC 1277 accounts for a staggering 60% of its bulge's mass. This is not just a slightly overweight giant, this is a cosmic anomaly of epic proportions. Imagine if a human heart made up more than half of a person's body weight. That is the level of imbalance we are seeing. How could such a thing form? One leading theory paints a dramatic picture. Perhaps this black hole did not grow slowly over eons by steadily feeding on gas and stars. Instead, it might be a primordial black hole, born impossibly large from the collapse of a vast cloud of gas in the universe's chaotic first moments. This would be a different kind of monster entirely, a relic from a time before galaxies even properly existed, around which the galaxy of NGC 1277 later assembled. Another possibility is that this galaxy is the survivor of a frenzied era of collisions, a cosmic packrat that accumulated an enormous black hole through a series of galactic mergers, but then, for some unknown reason, stopped forming new stars. Its bulge remained small and stunted, while the black hole it inherited was already a titan, leaving us with this bizarre, overmassive fossil. The implications ripple outward, forcing us to re-evaluate everything. If one galaxy can break the mold, how many others have we misjudged? Our own Milky Way's quiet central black hole now seems even more peculiar by comparison. Is Sagittarius a star unusually small for our galaxy, or is NGC 1277's giant the true oddity? This single galactic neighbor suggests that the paths black holes take to power are far more diverse and mysterious than we ever dreamed. It forces a profound re-evaluation of the supposed co-evolution of galaxies and their central black holes. What other ancient giants are hiding in plain sight, silently challenging the foundations of cosmic structure? Wrapped around our galaxy like a faint cosmic ribbon lies a structure of staggering scale. The Monoceros Ring is a vast, looping stream of stars located in the constellation of Monoceros, the unicorn, and it presents astronomers with a fundamental puzzle. Is this ring the ghost of a devoured dwarf galaxy, or is it a part of our own Milky Way, twisted out of shape? The debate over its origin forces us to question the very architecture of our galactic home. One compelling theory sees this ring as the latest chapter in our galaxy's violent history of cannibalism. In this scenario, a small, companion dwarf galaxy ventured too close billions of years ago. The Milky Way's immense gravity stretched and shredded it, pulling its stars into a long, looping tidal stream that now orbits far beyond the main galactic disk. This would make the Monoceros Ring a sibling to the other stellar streams we see, but on a far grander and more coherent scale, a gigantic celestial bracelet forged from the remains of a vanquished neighbor. The competing theory offers a radically different perspective. Perhaps the ring is not an external ghost at all, but our own flesh and blood. This idea suggests it is part of the Milky Way's outer disk itself, but a disk that is not flat and pristine. Instead, gravitational interactions with passing dwarf galaxies or with the surrounding dark matter halo have caused the outer edges to warp and flare dramatically. Picture a thin vinyl record left in the sun, its outer rim buckling and twisting upward and downward. The Monoceros Ring, in this view, is simply the crest of one of these immense, rippling waves of stars, a part of our own galaxy that has been flung far from the main plane. Distinguishing between these two stories is incredibly difficult from our vantage point deep inside the galaxy. The primary challenge is distance. Measuring the precise distances to millions of faint stars in the ring is a monumental task. If the stars in the ring all share a common, distinct chemical fingerprint, rich in ancient, primitive elements, that would be a strong signature of an extragalactic origin, a tag identifying them as foreigners. If, however, their chemical makeup closely matches that of stars in our own outer disk, it would powerfully support the idea that the ring is a warped part of ourselves. Current data tantalizingly hints at both possibilities, leaving the mystery wide open. The ring's true nature holds profound implications. If it is a cannibalized galaxy, it reveals a much more dramatic history of recent mergers than we previously thought. If it is a warped disk, it means our Milky Way is far more dynamic and fragile, its shape easily perturbed by gravitational forces. This single, faint structure of stars forces us to decide if we are looking at the ghost of a long-dead companion or the distorted mirror of our own galactic self. These pulsating stars are the lighthouses of the cosmos, guiding us across the vast ocean of space. Cepheid variables have a special talent, a rhythmic brightening and dimming that is perfectly synchronized with their true intrinsic brightness. This period luminosity relationship makes them one of the most important tools in astronomy, a fundamental rung on the cosmic distance ladder. By measuring how fast a cepheid pulses, we can know exactly how bright it truly is, and by comparing that to how dim it appears from Earth, we can calculate its distance with remarkable precision. It was cepheids that first revealed our universe was expanding, proving that other galaxies existed far beyond the Milky Way. But what happens when these trusted guides start lying? A growing number of these stellar metronomes within our own galaxy are behaving strangely, their pulses falling out of sync with the established rhythm. Some pulse with a different brightness than their period suggests they should. Others show chemical compositions that do not match their pulsation patterns, as if the star's internal orchestra is playing from the wrong sheet of music. These anomalies are more than just celestial quirks. They are cracks in the very foundation we use to measure the universe. What could cause a cepheid to break the rules? One strong possibility involves an unseen partner. If a cepheid is in a binary system, the gravitational tug of its companion star could subtly alter its pulse, distorting the clean relationship between period and luminosity. We would be measuring the heartbeat of a conjoined twin, not a single star. Another theory points to powerful magnetic fields churning within the star itself. A strong internal magnetic field could act like a rigid skeleton, changing how the star expands and contracts, and therefore changing the timing and intensity of its pulse. The most profound explanation, however, is that we simply do not fully understand the inner workings of these giant stars. Our models of stellar physics, while sophisticated, are still approximations. The complex interplay of nuclear fusion, convection, and elemental mixing in the searing hearts of these giants might be more complicated than our equations can capture. Each anomalous cepheid is a direct challenge, a piece of experimental data that our theories cannot yet explain. The stakes could not be higher. If our understanding of cepheids is flawed, then every cosmic distance we have measured using them carries a hidden uncertainty. This includes our calculation of the Hubble constant, the rate of the universe's expansion. The mysterious tension between different measurements of this expansion rate might, in part, be traced back to these misbehaving stars in our own backyard. Our most trusted cosmic landmarks are showing us they have secrets, forcing us to question the very map we have drawn of the expanding cosmos. Even the grand scale of our own galactic home is dwarfed by structures so immense they challenge the very definition of the universe. The Hercules Corona Borealis Great Wall is not merely a cluster of galaxies, but a colossal filament, a vast cosmic thread woven from countless galactic clusters stretching for an astonishing 10 billion light-years across the observable universe. This is not an object in space, it is a continent of space, a structural feature of the cosmos so large it should not, according to our foundational principles, exist. The cosmological principle, the idea that the universe is smooth and uniform on the largest scales, begins to crack under the weight of such a discovery. How can the universe be the same everywhere when one single structure encompasses such a significant fraction of everything we can see? This great wall is a paradox of scale, a feature so vast it seems to question the uniformity of the cosmos itself. The mystery deepens when we consider our own place within this grand tapestry. Some astronomers propose that the gravitational pull of this distant, unimaginably massive wall is not just a remote curiosity. It might be the ultimate source of the great river we are a part of, the primary force behind the mysterious flow of thousands of galaxies, including our own local group toward the Great Attractor. This idea suggests the Great Attractor itself is not the final destination, but merely a waypoint, a local concentration of mass caught in the same immense current, all being pulled toward the gravitational dominance of the Hercules Corona Borealis Great Wall. Our million-mile-per-hour journey through the void could be a small part of a far more immense pilgrimage. Yet, not all scientists are convinced this Great Wall is a real, coherent structure. The central challenge is one of perspective and mapping. When we chart the positions of galaxies across the sky, we are looking through a veil of dust and stars within our own Milky Way, a zone of avoidance that can create artificial voids and false groupings in our data. Could this apparent wall be a statistical fluke, a chance alignment of distant galactic clusters that only looks like a connected structure from our particular vantage point? Is it a true cosmic landmark, or simply a pattern our brains have imposed on the randomness of the universe? The debate rages, fueled by ever more precise maps of the distant cosmos. The resolution of this mystery holds profound implications. If the Great Wall is real, it forces a dramatic rewrite of our cosmic rulebook, suggesting that the universe organizes itself on scales we once thought impossible, with gravitational influences spanning distances that defy comprehension. If it is an illusion, it reveals the limits of our own perception, a cautionary tale about the patterns we might imagine in the dark. Either way, it pushes the boundaries of what we believe is possible, reminding us that the largest structures in existence might still be hiding in plain sight. Our cosmic neighborhood feels emptier than it should be. The most powerful computer simulations of the universe, based on our best understanding of dark matter, paint a very specific picture of our galactic surroundings. They predict that the Milky Way's immense gravitational pull should have captured thousands of small dwarf galaxies, swarming around us like a cloud of fireflies. Yet, when we actually count them, we only find about 60. This glaring mismatch between prediction and reality is one of cosmology's most persistent headaches, known as the missing satellite problem. Where are the hundreds, even thousands of tiny galaxies that our models insist must be there? The solution might be that they are, in fact, all around us, but they are hiding in the darkest possible way. The leading theory suggests that the vast majority of those predicted dark matter clumps did form, just as the simulations show. However, they were simply too small and too weak to ever ignite the process of star formation. Imagine a cloud of hydrogen gas held together by its own tiny pocket of dark matter, but so diffuse and lightweight that it could never collapse under its own gravity to birth a single star. These would be dark galaxies, ghostly halos of pure dark matter and primordial gas, drifting silently through the galactic halo, completely invisible to our telescopes. Another possibility involves the violence of the early universe. In the chaotic environment of a young galaxy, the first generations of massive stars lived short, explosive lives. When they went supernova, these stellar detonations unleashed colossal winds, blasting gas out of the small, vulnerable dark matter halos. This process, called supernova feedback, could have robbed these potential galaxies of their star-forming fuel before they even got started. It is a cosmic case of having the foundation for a house, but having all the building materials blown away by a hurricane. The smallest halos were the most susceptible, stripped bare, and left as barren, dark matter islands. The search for these missing satellites is now a major driving force in astronomy. New, incredibly sensitive surveys are scanning the sky, looking for the faintest possible glimmers. They are hunting for the occasional lone star that might have been kicked out of a dwarf galaxy, a tracer of a larger but invisible structure. Others are searching for the subtle ripples these dark matter clumps would create as they drift through the gas of the galactic halo. Perhaps the most tantalizing possibility is that this problem is not about galaxies at all, but about dark matter itself. What if our fundamental assumption about dark matter is wrong? The standard model, known as cold dark matter, assumes the particles are slow-moving and heavy. But if dark matter were warmer or more interactive with itself, it would not clump together as readily on small scales. This would naturally lead to far fewer small halos, neatly solving the missing satellite problem by changing the nature of the phantom itself. The resolution to this cosmic census will fundamentally reshape our understanding of everything, from the smallest building blocks of the cosmos to the largest structures within it. Are we surrounded by a hidden population of dark galaxies, or is the universe telling us that the ghost we have been chasing is stranger than we ever imagined? Deep within the heart of the Milky Way, a colossal structure is picking up speed. Our galaxy is not a perfect pinwheel, but a barred spiral with a thick, dense bar of millions of stars cutting through its center. For a long time, we assumed this bar rotated at a steady, predictable pace, a slow cosmic waltz governing the inner galaxy. New data, primarily from the Gaia Space Observatory, is shattering that assumption. By tracking the individual motions of countless stars within this bar with unprecedented precision, astronomers are finding compelling evidence that it is spinning significantly faster than our models ever predicted. This is not a small correction. The pattern speed of the bar, the rate at which its gravitational structure rotates, is a fundamental property that dictates the rhythm of life for stars in the inner galaxy. A faster bar creates stronger gravitational resonances, like the rhythmic pushes a child receives on a swing. These resonances can fling stars inward toward the galactic center or outward toward the spiral arms, effectively redistributing the galaxy's stellar population over time. This stellar migration changes the very architecture of the Milky Way, influencing where new stars can form and how the spiral arms are sustained. The implications reach even further into the realm of the invisible. The speed of the bar is a direct probe of the galaxy's gravitational field in its inner regions. A faster rotation suggests that the tug of gravity there is stronger than we thought, which in turn points to a higher concentration of mass. Since we can see all the visible stars and gas, the extra mass must be hidden. This is a powerful new clue in the hunt for dark matter, suggesting it is not just in a diffuse halo around the galaxy, but densely packed toward the center, its gravitational grip helping to whip the central bar to a faster tempo. The debate is now fully engaged. Is our measurement of the bar's speed correct, or are we misinterpreting the complex motions of stars in that crowded region? If it is correct, does it force us to revise our models of how bars form and slow down over billions of years? The spin of this central structure is more than a curiosity. It is a key to unlocking the true distribution of mass, both seen and unseen, in our galactic core. What other secrets will a faster spinning bar reveal about the forces that have shaped our cosmic home? This vibrant cosmic nursery, glowing with the fiery red light of ionized hydrogen, is far more than a beautiful cloud. The Cat's Paw Nebula is a stellar factory, a place where new suns are being built before our very eyes, yet the precise mechanics of how a star is born remain one of the galaxy's most intimate secrets. The journey from a diffuse, cold cloud of gas and dust to a blazing, self-sustaining star is a cosmic battle between gravity and pressure, and gravity should not win as easily as it seems to. This is known as the final parsec problem. To collapse, a cloud must shed its immense magnetic field and rotational energy, a process that theory suggests should be incredibly inefficient, taking far longer than the observed lifespan of these nebulae. It is as if a building were collapsing, but instead of falling straight down, it had to slowly unwind itself first. So how does nature cheat this slow cosmic death spiral? The answer seems to lie in a violent and chaotic ingredient, turbulence. Within the nebula, supersonic winds and shockwaves from nearby supernova can violently stir the gas, creating dense knots and pockets where gravity can get a stronger, quicker grip. Think of it like stirring a cup of coffee. The swirling motion naturally brings particles together, allowing them to clump and fall. Magnetic fields also play a crucial but poorly understood role, acting not just as a rigid skeleton that supports the cloud, but perhaps as a complex web of channels that guides material inward, helping the baby star or protostar to gather mass against all odds. Yet, even when a star does manage to form, a new puzzle emerges, the luminosity problem. When astronomers calculate how bright a newborn star should be based on its mass and age, their predictions often far exceed what we actually observe. These young stellar objects are curiously, persistently dim. It is like expecting a roaring bonfire and finding only a smoldering ember. Where is all that missing energy? One possibility is that the star is not forming in a simple, spherical collapse, but is instead accreting its material through a complex disk. If mass falls onto the star in irregular, episodic clumps rather than a steady rain, the energy release might be very different. Alternatively, powerful magnetic fields might be redirecting the infalling material, channeling it toward the poles in focused jets that shoot out into space, robbing the central protostar of the energy we would normally see as visible light. This means our most basic picture of a star's first breath, a steady gathering of material that grows steadily brighter, is likely a dramatic oversimplification. The faint glow of a newborn sun in the Cat's Paw Nebula is not a sign of weakness, but a clue that the very first chapter of a star's life is a story of chaos, magnetic labyrinths, and energetic outbursts we are only beginning to decode. Far beyond the last known planets, in the profound cold where the sun is just a particularly bright star, lies the solar system's final frontier. The Oort cloud is a hypothetical sphere of trillions of icy bodies, a vast reservoir of primordial rubble left over from the solar system's formation. We have never seen a single object in the Oort cloud directly, its existence inferred entirely from the long-period comets that occasionally streak into the inner solar system. These icy wanderers, with orbits lasting thousands or even millions of years, are messengers from this invisible shell, and their arrival hints at a dynamic, chaotic environment shaped by forces far beyond the sun's influence. The quiet rhythm of their journeys is orchestrated by the Milky Way itself. As our solar system orbits the galactic center, it bobs up and down through the galactic plane. This motion creates a tidal force, a gentle but persistent gravitational pull from the collective mass of the galaxy's disk. This galactic tide acts like a slow hand, stirring the outermost Oort cloud and periodically nudging icy bodies from their stable orbits, sending them on a long fall sunward. These tidal tugs are amplified by the silent passage of other stars. Every so often, another star drifts relatively close to our solar system, its gravity reaching into the Oort cloud like an unseen giant plucking strings on a cosmic harp, dislodging comets and altering their trajectories for eons to come. But could there be more than just ice and rock in that unimaginable darkness? The sheer number of objects predicted to be in the Oort cloud and the peculiar clustering of some comet orbits has led to a tantalizing speculation. A hidden planet, perhaps with a mass similar to Earth or even Mars, might be orbiting out there in the perpetual twilight. This would not be a gas giant like Planet 9, but a smaller, stealthy world of rock and ice, its presence betrayed only by the subtle way it shepherds the cloud of comets around it. An even more exotic possibility exists. Some scientists have proposed that the Oort cloud could be a cosmic museum, capturing rogue planets that were ejected from other star systems in the galaxy's chaotic past. Our sun's gravity could have snared one of these wandering, orphaned worlds, locking it into a distant, lonely orbit. We would have an alien exoplanet right here in our own solar backyard, a permanent refugee from a foreign sun. Finding any of these objects, whether a hidden terrestrial planet or a captured interstellar wanderer, represents one of the greatest technological challenges in all of astronomy. At such immense distances, these bodies would reflect virtually no sunlight. They are not just dim, they are effectively black, lost against the background of the universe. Spotting one would be like trying to see a single lump of coal in the pitch black of a deep cave from miles away with a flashlight that is failing. Our largest telescopes would struggle to find such a faint, slow-moving speck, and even if they did, confirming its orbit would take decades of painstaking observation. The Oort cloud remains the ultimate ghost in our celestial machine, a borderland between our solar system and the wider galaxy, its true population and secrets locked in frozen darkness, waiting for a messenger to begin its million-year journey toward the light. Even our most carefully engineered probes can carry secrets into the void. As the Pioneer 10 and 11 spacecraft sailed beyond the orbit of Pluto, their precise trajectories told a strange story. Each was slowing down by a minuscule yet persistent amount, a deceleration so tiny it was like having an invisible hand gently pressing on the brakes. This was the Pioneer anomaly, a drift so slight it could have been dismissed as a glitch, but it persisted year after year, a constant, unexplained tug acting from the sun's direction. For decades, this tiny whisper in the data haunted physicists. Was it a sign of some unknown drag from tenuous interstellar dust? Could it be evidence of a flaw in our understanding of gravity itself? A hint that Einstein's theory needed a subtle modification at the vast scales of the outer solar system. The anomaly became a specter of new physics, a suggestion that our deepest cosmic laws were incomplete. The solution, when it finally came, was not written in the stars but in the spacecraft's own blueprints. The culprit was heat, but not from an external source. The plutonium in the probe's power generators produced a steady stream of warmth, and this thermal radiation was not escaping the spacecraft symmetrically. More heat was radiating from the back of the dish-shaped antennae than from the front. This tiny imbalance created a recoil force, a faint but constant pushback toward the sun, perfectly accounting for the mysterious deceleration. The anomaly was not a flaw in the cosmos, but a lesson in engineering humility. It reminds us that when we push the boundaries of measurement to such incredible precision, we begin to hear the subtle sounds of our own machinery. Yet its legacy endures as a powerful warning. For years, an entire field of theoretical physics was nudged in a certain direction by the ghost of a few watts of excess heat. It proves that the greatest mysteries are sometimes hiding in the plainest of places, and that the path to understanding the universe requires us to first understand the tools we send into the dark. Our galaxy's long history of stellar birth and death has left a chemical fingerprint on every star, a cosmic record of its violent evolution. Yet this very record holds a contradiction so fundamental it is known simply as the G-dwarf problem. Picture a vast celestial census of stars like our own Sun, the so-called G-dwarf stars in our local galactic neighborhood. According to our most straightforward models of how galaxies evolve, we should be surrounded by a huge number of ancient metal-poor stars. The term metal in astronomy means any element heavier than hydrogen and helium, the forged remains of countless supernova explosions that have slowly enriched the galactic gas over billions of years. Simple logic suggests the first stars to form should have been composed of almost pure primordial hydrogen and helium, with very few of these heavier metals. As they died, they seeded the cosmos with new elements, so each subsequent generation of stars was born from slightly richer, more metal-filled gas. If the Milky Way's disk formed in a single, isolated event from a closed box of gas, we should now see a wide spectrum of stars, from the extremely metal-poor to the extremely metal-rich, with a great many of those ancient, pristine suns still shining today. But when we count them, they are not there. The metal-poor G-dwarfs are conspicuously, bafflingly rare. Where did all the ancient stars go? This missing population points to a dramatic revision of our galactic story. The Milky Way's disk could not have formed in isolation. One compelling solution is that the gas which originally collapsed to form our galactic disk was not pristine at all, but had already been pre-enriched by an earlier, more violent generation of stars that lived and died fast in the galaxy's chaotic infancy. This would mean the very first disk stars were already born with a significant metal content, skipping the initial, purely primitive phase entirely. Another, perhaps more dynamic, explanation involves the galaxy continuously feeding. Over its lifetime, the Milky Way may have been accreting vast, fresh reservoirs of primordial hydrogen and helium gas, either siphoned from its own halo or stripped from smaller, cannibalized galaxies. This constant inflow of pristine fuel would have diluted the interstellar medium, slowing its overall metallicity increase and effectively hiding the most metal-poor stars from our modern senses. The G-dwarf problem is more than a statistical quirk. It is a direct window into the galaxy's breathing rhythm. It reveals a system that is not closed and static, but open and dynamic, constantly exchanging matter with its environment in a great cosmic cycle. This continuous inflow of fresh gas is, ironically, what allows for the ongoing birth of new stars, while its mixing with the enriched ashes of dead stars creates the specific chemical conditions that made our own sun and our own planet possible. The very reason we find so few of those primordial stars is the same reason we are here to look for them, a paradox written in the elements that make up our world. An invisible rain from deep space is falling through you at this very moment. Galactic cosmic rays are not rays of light, but a torrent of high-speed atomic shrapnel, primarily protons and the nuclei of heavier elements, hurtling across the galaxy at nearly the speed of light. They bombard our planet from every direction, a constant, silent sleet of matter that has puzzled scientists for over a century. The central mystery is one of pure power. Where in the cosmos are the natural accelerators capable of launching particles with energies millions of times greater than anything produced in our most advanced particle colliders, like the Large Hadron Collider? The hunt for these cosmic engines has led us to some of the most violent events in the galaxy. For decades, the prime suspects have been the expanding shock waves from supernova explosions. When a massive star dies, it blasts its outer layers into space at incredible speeds, creating a colossal, spherical shock front that rips through the surrounding interstellar gas. Think of this shockwave as a gigantic natural particle accelerator. Charged particles like protons can become trapped between the advancing magnetic fields on either side of this shock. As they bounce back and forth, they gain a little more energy with each pass, like a surfer being repeatedly pushed by an endless wave, until they are eventually flung out into the galaxy at a significant fraction of light speed. This theory is elegant, but for a long time it was just that, a theory. The smoking gun was missing. We needed to catch these accelerators in the act. Recent observations have finally provided that crucial evidence. By studying the gamma-ray light and X-rays emitted from several well-known supernova remnants, astronomers have detected the specific energy signature of protons being accelerated to these tremendous energies. They are essentially seeing the glow from the cosmic ray factory itself. Yet, even as one mystery begins to clear, a deeper one emerges. While supernova remnants appear to be the source for the vast majority of galactic cosmic rays, they cannot easily account for the very highest energy particles we detect, the ultra-high-energy cosmic rays. These rare, monstrous particles carry as much energy as a professionally thrown baseball, all compressed into a single, subatomic speck. Their origin is so enigmatic that some scientists have looked beyond our galaxy for an explanation. Could the cataclysmic mergers of neutron stars, the engines of short gamma-ray bursts, be capable of such feats, perhaps the gargantuan jets erupting from active galactic nuclei, where supermassive black holes are actively feeding, are the only accelerators powerful enough to produce such extreme particles. The puzzle of galactic cosmic rays is a layered one. We are now confident that the expanding shells of dead stars are the primary source of this cosmic rain, a fundamental discovery that connects stellar death to the very particle background of our galaxy. But the existence of those rare, ultra-high-energy outliers tells us that the universe still holds even more powerful and violent engines, whose identities remain just out of reach. What unimaginable cosmic events are capable of hurling a single atomic nucleus with the force of a major league fastball across the vast emptiness of intergalactic space? Even the emptiest regions of our galaxy are not truly empty. According to our deepest theories of physics, the vacuum of space itself should be a seething, bubbling foam of virtual particles, constantly flickering in and out of existence. This quantum activity should endow every cubic centimeter of nothingness with a staggering amount of energy, a force pushing outward that we call vacuum energy. The calculation for this energy density is straightforward, and the result is a number so colossal it defies all reason. It predicts a value 1 followed by 120 zeros times greater than what we actually observe from the expansion of the universe. This is not a small error. It is the most spectacular failure of a prediction in the entire history of science. If the theoretical value were correct, the repulsive force of this vacuum energy would have been so immense that it would have torn every atom, every star, and every galaxy apart in the first instant after the Big Bang. Our universe and our Milky Way within it would simply not exist. The fact that we are here to ponder this means something is profoundly wrong. This glaring mismatch is known as the vacuum catastrophe, and it points to a fundamental flaw in our understanding of reality, a crack in the bridge between quantum mechanics and gravity. The observed effect of this mysterious background energy is what we call dark energy, the force driving the accelerated expansion of the cosmos. Its true value is not enormous but infinitesimally small, a whisper of a push that only dominates the universe on the largest scales. Why is the energy of the vacuum so close to zero, yet not perfectly zero? Is there a cancellation mechanism, an unknown symmetry in the laws of physics that perfectly balances the books, leaving behind only the tiny residue we call dark energy? Or is our entire concept of vacuum energy fundamentally mistaken? Every star you see in the night sky, every spiral arm of our galaxy, exists within this enigmatic background. The very space that allows the Milky Way to hold its shape is simultaneously stretching the cosmos apart on a grander stage. Solving the vacuum catastrophe is not just an abstract puzzle. It is a quest to understand why there is a universe for our galaxy to call home at all. What undiscovered principle keeps the void so quiet, allowing the delicate structures of our cosmos to form and flourish? All these mysteries, from the whispers of dark matter to the shouts of fast radio bursts, are threads in a single grand tapestry, the ongoing story of our galaxy. But every story has an ending. The ultimate mystery of the Milky Way is its final chapter, a destiny written in the slow, relentless pull of gravity. 4.5 billion years from now, our galaxy will meet its closest neighbor in a dance of cosmic proportions. The Andromeda Galaxy, a faint smudge of light in our current night sky, is on a direct collision course with us, approaching at a speed of 250,000 miles per hour. Computer simulations of this future cataclysm paint a spectacular picture. The two spiral giants will not hit each other like a pair of cars in a cosmic wreck. Instead, they will perform a gravitational pas-de-deux, first swinging past each other in a close encounter that will warp and tear their spiral arms into spectacular, streaming tails of stars. They will then swing back, drawn together by their mutual gravity, and merge into a single, enormous blob-like galaxy. astronomers have already given this future titan a name, Milky. Yet for all the precision of these simulations, profound uncertainties remain. The fate of our own solar system is one of them. The spaces between stars are so vast that it is very unlikely our Sun and its planets will collide with another star during this merger. However, the gravitational chaos could easily fling our solar system out into the galactic halo or send it diving toward the new galactic center, a cosmic roller coaster ride with an unknown final destination. The other great unknown is the role of the Triangulum galaxy, a smaller spiral that is gravitationally bound to Andromeda. Will it be a mere spectator, or will it join the merger, creating a triple galaxy collision that further stirs the cosmic pot? The exact final structure of Milky is also a mystery. Will it be a standard elliptical galaxy or something with a more complex hybrid structure? This merged galaxy will shine for trillions of years, but its story does not end there. In the far, far future, as the universe continues its accelerated expansion driven by dark energy, all other galaxies will have receded beyond the cosmic horizon. Milky will be left utterly alone, a single, fading island of light in an ever-cooling, ever-darkening void. The stars within it will slowly burn through their fuel one by one until the last suns flicker out. The ultimate fate of our galaxy and all the mysteries it contains is to become a ghost in the darkness, a silent monument to a universe that was once full of light and wonder. From the silent pull of dark matter to the faint glow of the Fermi Bubbles, our journey through these 25 cosmic riddles reveals a galaxy that is anything but static. The Milky Way is a living, breathing entity, forged in ancient violence and shaped by forces we are only beginning to comprehend. We have stood at the edge of a black hole that barely whispers and raced alongside stars flung from the galactic core. We have traced the ghostly rivers of stellar streams and felt the immense tug of a void we call home. Each enigma, from the misbehaving Cepheid variables to the phantom of Planet 9, is a testament to a universe that thrives on mystery. Every answer we uncover does not bring an end to the wonder, but instead opens a door to a room filled with even more profound and fascinating questions. So we turn the final reflection over to you. Which of these galactic secrets left you the most astonished? Share your thoughts in the comments below. And if you enjoyed this voyage through the unknown, be sure to like, subscribe, and tap the notification bell so you can join us for our next exploration into the wonders of the cosmos.